Teaching can come.
Okay, so after the two previous lectures, which were about um, we now move to a different, slightly stronger logic. I mean, I said a lot about the resulting logic in a model, which is the L with respect to the extension of the logic by this. Okay. Were you all in my previous lecture?
I think I was right.
You were not.
It was this week or?
Yeah.
Yeah, I was.
Okay.
Sorry, but don't worry.
Now we go to a different logic. I mean, this is nice, but in a model, it's forcing absolute and everything, but it's rather small. It's closed and sharp, so it's not too small. But we don't know whether it has any measurable kernels, for example. The moment we suspect that maybe not. And we don't know for some reason whether CH is true. That model. So we sort of don't understand it enough. So okay, now this almost all quantifier. This is a second order quantifier. You can only those A in the family of countable subsets of M such that M, when it is expanded by A, and then well, like this, contains a club. So there is a club of countable subsets of this model. So this model is like M, and there's a club of countable subsets like this, and each one of them satisfies phi. So each one of them satisfies phi. Okay. Note that these subsets do not have to be, in some sense, elements of this M. These individuals A are elements of it, but these subsets are not elements of M. If M was a model, transitive model Z, it would be meaningful to ask, are they elements? But if M is a field, for example, it doesn't really make sense to ask if this S. So these come from V, and the club comes from V. So there are two things which come from V: the countable set and the club. Okay, but as a quantifier, it makes kind of perfect sense. And as I said in my colloquial lecture last week, this is completely axiomatic. It is. And what was kind of cute is that the only non-trivial axiom which you need is Fodor's lemma. You can write Fodor's lemma, but I won't go into. But Fodor's lemma is a complete axiom of this, and it is counterfeit compact, etc. And of course, the cofinality quantifier can be defined. We can say there's a club of S such that S is cofinal. in 5. Right, but of course this is the first one state, because S is the predicate, so this can be determined. If there is one cofinal omega sequence, then the principal field that's related by is I mean, is the plot. All subsets is contained. Now, I will define this. Okay. There is the old definition which I gave in my previous lectures, but now we give a different definition for the reason which is we briefly discussed already, that we don't know at the moment how to give a truth definition for this logic with this in the logic itself. I mean implicit truth definition. While for this we can give, for this we can give like for first logic an implicit truth definition, and that gives a canonical well order of this model which is but for this we don't know how to give an implicit truth definition at the moment for the following reason. Yes, we do have a variable for variables for countable subsets, but we cannot existentially or universally quantify over S. We can only quantify it in this sense. But if one uses the usual method, which goes back to first Stransky and kernel and then Craig and Porter, to how to define this implicit truth definition, you would need here the secondary variable, but three secondary variables, but we don't have three secondary variables, we just have this one operation. Okay. So therefore, we define it in a new way, using the J prime. J prime. Okay. Oh yes. And I use only limit ordinals as in Schindler's book. Is a rudimentary closure with respect to an operation which I call true of J prime alpha union J singleton, and for limit it's a union like this. Okay, so what it is, so this is a rudimentary closure. It means a closure under so-called rudimentary functions, which are written like Gödel functions, simple functions like union, forming ordered pairs, and so forth. But what is this TR? TR is the truth predicate, truth definition, and the truth definition is simply the following: it is a set of pairs beta phi a such that J prime beta with epsilon and the truth predicate up to beta satisfies phi a, this where phi x, and there are its only individual variables, belongs to the first belongs with a quantifier, and a bar belongs to J prime. So it is a recursive definition. This is defined in terms of its restrictions to earlier ordinals, and on each level it gives the exact truth definition of this. And it's here so as an operation. Now this satisfies. Okay, so CAA is a union of J prime alpha, and This satisfies CFC simply because there's a general result which goes back to Jensen and the next lemma in Schindler's book on set theory, that all these kind of structures satisfy there's a canonical well or okay. If we did this for the covenant quantifier, we would get exactly the same. So, but open question: is CAA the same as the old CAA, which I denote in the upgrade CO. The old CAA is defined using just the usual definition. And we don't know that, and we don't know whether the old CAA satisfies axial choice. Okay, so are you following? Do you know what I mean by this, or is it becoming a little bit?
I don't know what old C is.
What?
I don't know what old C is.
It is this. Everything which is definable in the logic in L prime, well, alpha L prime mu is union alpha less than mu. Alpha and C old AA is union of L prime. So this is the old definition. This is a Gödel definition of, except that Gödel has Facebook logic here. We first defined it this way, and we thought it is obvious that it satisfies choice, but Gabe Goldberg observed that it doesn't, that it's not clear. And now we don't know. And therefore this question. Is it now a bit clear? It's kind of intriguing question. How much choice can one prove here in this model? Yes, maybe everything and maybe something less, or is it consistent? So it is conceivable that consistency of CF implies consistency of this not satisfying maximum by force. Okay. Okay, so now the first dilemma, which shows a little bit of the nature of this. Suppose P is stationary preserving and G is generic. Then CAA V is the same as CAA PG. So you cannot change this model by stationary preserving force. On the kind of linguistic level, it seems obvious because we are talking about stationarity here, but in mathematics we go beyond the linguistic level. So we need a proof. And this is typical of this area that I'm talking about. Let's denote J double prime with the hierarchy for CAA in VG. So we're working in VG, we define hierarchy, and now we denoted working in BC like this. Then for all alpha j prime alpha is the same as j prime alpha. One can prove this by in induction on alpha, and then one comes to the successor stage, and one has to consider the rudimentary closure. The main thing which is problematic is PR, so one has to prove the preservation after all kinds of inductive assumptions. One has to prove the preservation of this. One can show that it is it's enough to prove this claim that if S subset of P less than omega 1 J prime alpha, and S belongs to B, then S is stationary. If and only if S is going B, if and only if S is stationary in BG. So this is what we have to look at, because we proceed by induction, so we can assume that we are looking at a graph on a set which is in the smaller, it is V, and the set is even in V, because we progress by induction on the complexity of the formula phi. But then comes this question whether some set is stationary or there's a club or not. And this, but this follows.
Sorry, could you give an example of why do we need the restriction to J alpha, to the subsets of omega of J alpha prime? Because if I have, as you said, on the linguistic level, if I have a stationary subset of V and force stationary, so preserving force. Yes.
Okay, so what is the question? I was thinking about something.
So why do you need the restriction to subsets only of J alpha prime?
Because otherwise it's a proper force.
Yeah, so sorry, I was absent-minded. I made the wrong assumption, is sigma closed.
Okay.
So it is more than stationary, so it is proper, and it's it gives both ways. Well, I assume this, and then I move to go to alpha plus omega. So then I look at subsets subsets of this, but by induction hypothesis it is the same as that. So it doesn't matter which one I put here as prime.
Yeah, but you will have that only from properties essentially. So, I mean, this claim,
One direction from proper,
I think.
the other direction from sigma closed, that cloud contains a cloud.
Okay.
And now, a very fundamental concept here. Yes, okay, so it reminds me. And Menachem Magidor. Yeah, because I remember that Magidor inventing this club determinism. Okay. Club determinism. In or CD is the following claim that for any alpha, any phi x, s x t in the logic with the A quantifier and any A in J prime alpha and any countable D in J prime alpha. J prime alpha satisfies almost all S phi S A P or almost all S not phi S A P. Okay, so if you have a definable set of countable subsets, then either it contains a club or its complement contains a club. What does that mean? No bistationary sets. No sets which are stationary and co-stationary, which are definable. No definable bistationary sets. This is a kind of radical requirement, but it is extremely helpful because it means that this quantifier becomes much more regular somehow. Because whenever I find a stationary, some phi that is satisfied by stationary many sets, which is kind of easy because I just intersect every club. So if I find a stationary set, then club determinacy gives me immediately a club. Now, being stationary is kind of phi 1, because you say that for every club. While containing a club is extensor. And everyone in logic knows that if you can move from universal to extensor, it's extremely powerful thing. So we use that, for example, to prove that uncountable regular cardinals of V are measurable in this model. This is approaching absolute, and it's real star countable sigma 1 3, and CHOs, in fact CCH. So all these follow from club determinism. Therefore, it's very interesting to know that this club determinacy follows from just the assumption of a proper class of Hilbert. And it can be replaced by proper constancy. Now the proof of this is long and complicated, but I will give an idea, a rough idea. So,
Do you have counterexamples in L?
what's that?
Do you have counterexamples in L to club determinacy?
Yes. Yes.
Like like the question is, of course, to what extent are the assumptions necessary?
It is. This is well. So the counterexample in L. This certainly implies, for example, zero sum, but I don't know.
Okay.
I don't know how to do it, but it is here. This can be replaced by for every set X that's a sharp of X. No, there's a M1 sub of X. And exists, then it is enough. But we don't know exactly what is the consistency, but we think that it is something on that. So, yeah.
Can you replace the alpha primes by arbitrary sets x? Instead of j alpha prime, that you have any or any.
Yeah, I will.
In formulation.
You see the
Yes, yes, I think here, if this X is in V. Yes, so the proof is trivial, so you can see, yes, so,
yeah, but
it can be an arbitrary set X in V.
Yeah, that's for the claim, but for cloud determinacy.
Oh,
The bottom of the bottom of the book.
oh, sorry, okay. No. But again, I don't know, cannot explain why, but it is, yes, I think I know, but I know I know my salary, but if you ask what is my salary, I couldn't give it to you. I don't know. It's a philosophical difference. So there is this was studied separately of this question whether a model satisfies club determinacy. And they are called determined models, and a lot of models are determined, and Salah made the proof that every countable theory here has a determined model and so forth, but there are non-determined models. It's just cannot immediately say. But we only need this, that's why we also formulated that. I don't think I could prove it for certainty. So, suppose the club determinacy fails, so then so first, club determinacy means that there is first note that this J prime alpha for alpha less than omega 1 is just held out. This quantifier is completely useless in countable models, so you have to go in order that this says anything. You have to go above omega 1 or B. Now, if there is an alpha so that this fails, then there are arguments involving, for example, delta 1, 2 is omega 2, that they have to force delta 1, 2 is omega 2, then, so that we can put this between omega 1 and omega 2, and also that we can get certain parameters. Now we take a unicardinal after all this preparatory forcing, also to get this the first counter example between omega 1 and omega 2, we may have to do some forcing. So then there's the unicardinal. So then we go into this model M like this. So here is I, here is I, here is delta, which is I omega 1. And so suppose this is P, is this offending? Yeah, it's bistationary set here. So now P is, now JP is somewhere here. And then we have this PG. The idea is the following. We show that, so if we have here this kind of hierarchy, then here, let's call it hierarchy J double prime, gamma like this. Then, and let's call here J triple prime gamma is the AA less than delta hierarchy. So this means that we replace the AA quantifier by a quantifier which says that there's a club of a club of not countable sets but sets a lot smaller than delta. And now it turns out that
What do you mean by that? The closed under column function or being a class or the other definition closed under?
I didn't understand this.
So there are various notion of class for a set when that concentrates of sets of class of size. So which one are you taking there?
On delta, you mean?
Yes.
Closure
under a column function.
Yes.
So like the one in the stationary tower.
Yeah, yes. So then what happens is that, and the main thing to prove is that say double prime beta, which is in M, is actually J triple prime beta in B for beta less than or equal to R. And to prove that, we need some new things about stationary tower forcing, and the following fact is: suppose S subset of offset less than delta of X is stationary in B, then S is stationary in BG. For any X, any X of such. And it appears that this was not known, but anyway, we prove it, and the proof goes directly into the definition of stationary tower force. Okay, so, but that means that this, you see, this is in V, and this is in M. M uses the generic of the stationary tower, so M is not contained in V. But this side is in V, so this actually is in V. This.
Okay. You will have delta 1 equals omega 2 and omega 3 speed. But neither PFA nor PC. Was PFA by delta 1 equals omega 2?
No.
So what do you mean by delta 1 equals omega 2?
What do I mean by it?
Because none of your hypotheses seems to imply delta.
Yes, but you took a nap when I said how I get.
Yeah, so I wasn't paying attention.
Yeah.
So you increase some forcing.
Yes, I do first suppose. Because I have Woody cardinals,
Right.
measurable cardinals. So there's a result of Shelah, there's a stationary reserve forcing, which forces delta 1 to store Woody or Shelah, it's not clear. Who's the forces. So I force, that's why I need a proper class, because I need after that forcing still a Woody cardinal. But then you need. Yes, but I also need the forcing which collapses alpha to omega, size omega 1. A priori, this alpha can be anywhere, but I collapse it to size R1 without changing essentially anything. And then I want the even after that forcing, which collapse. Okay. So now okay, so now I can use essentially, I can use this set, let's call this, I can use that as a forcing condition in the, it is in V, so I can use it in the, I haven't said what this generic G is. I can, whatever generic I get, take, this is the same same S. But I can change the generic by putting omega 1 into this or leaving omega 1 out. I mean, into the image by forcing inversion tau forcing below S or below the complement, because this is a bistationary set. So then in the image omega 1 is in or out, but it cannot be both. So
That's
that's
you force with the full stationary tower, because
no
that is,
countable.
but that is now concentrating on sets of large size.
Yes, but I don't force with that. No, this is just a fact. So let's see. This is just a fact which I use in the proof. But this S here is a set of countable subsets of delta. It's not actually of delta, but you have to take a bisection into delta.
But this S exists in the ultra power, not in B.
Yeah, that's the trick. It's because of this.
So in the ultra power consists of countable sets, but as a set exists in B.
Yeah,
But then you cannot use it in the stationary tower forcing, because the condition in stationary tower forcing are countable sets countable in B, not countable in A.
yeah, but this is a set of countable sets in B, because it comes from this fact that these are the same.
But there you were using the quantifier over less than delta, not over. So this I don't follow.
So what it has, maybe.
S is the pointwise image of P, is JP. S is equal to JP.
Yes, so in this triple J, I use this different quantifier, and this so I'm jumping over many steps, but maybe I jumped over too many steps. When I have this, then I take the set of countable subsets of delta,
Which belongs to S.
such that x intersect omega 1 belongs to S. There is a construction like this, which reduces, which allows me to compute from this S a set of countable subsets of
Maybe you know that S is splitting the countable subset of delta in two pieces, and one of them has to be stationary, so either the piece in S or the complement is going to be stationary, or both of them. I don't know.
Okay, I don't want to get stuck in this. the main thing is that we do a lot of work to prove this, and in that way we can make this of this smallest counterexample. It's very important that it's the smallest counterexample to be an element of M, which actually is an element of V, and then we can get from that the Fossil condition for this tower, counterpose tower, which shows that it cannot be in V, that it really depends on the genetic, and that's the contradiction, and therefore we cannot have here this. Yeah, I wasn't going to talk about this, so I'm a little bit from the by the way, there's a game definition of this AA quantifier. Which is the following: for all x0 there exists x1, for all x2 there exists x3, so that phi holds of x0, x1, like this. So you can test this by playing a game and asking whether the step you produce in the game satisfies phi. So this graph determinism says that this game is perfect. So for all of this, first, if assume CV first, if kappa is regular, then kappa is measurable cardinal in CAA. That's because you can take an obvious. Okay, so let alpha be big, and then you define F is those subsets of kappa such that X belongs to J prime alpha and J prime alpha satisfies almost all S. Supreme of S intersect kappa is in X. Now this is a normal filter, and this graph determinism implies that it's a positive. Second consequence, theory of CAA is possible. Was an absolute. This uses the following fact that if we have a stationary tower forcing then CAA in the inner model M is CA the same as CAA less than delta in V. We already discussed this.
But do you, do you know that from CD there, do you have enough strength to have stationary tower with the right properties, or do you assume something more?
How am I so absent-minded? Of course, you need proper class Murica. So let's put here proper class Murica.
Okay.
Because you have to have Unigarden after the post. While for the first you only got the Now I want to go into the proof of that because it is exactly the same as for this modifier, that you start two stationary towers, one before the forcing and then the one after the forcing, and then they converge to the same, and to the same, which is this here. If the Woody Gardner is above the force. And okay. So now I move to the new theorem.
But you don't have a canonical embedding of CAA as computed in B into CAA as computed in BG. So you just know that the two theories agree, but not that you can embed one into the other.
You
Bit
have
like the model.
from V and from VG, you start a stationary tower, and then they both converge to
That one. So
Yeah.
they have the same theory, but you don't have an elementary embedding of the
Yeah.
one of B into the one of BG.
So these the embeddings from a stationary tower are elementary. So if you have from here elementary to star and from M prime elementary to M star, and if this is like this, then it follows from this that this is actually okay, so it takes some elements here, some mapping to here. No, you don't have that now. At least I don't see it immediately, but it could be some. So I see it. So now this I will prove with the remaining 15, 10 or 15 minutes. Because that is a different kind of proof. So I define what we call AA. And it is of the form M, also J alpha epsilon P star and some predicates like this. So this is a sequence of predicates P gamma gamma. Unary predicates. So first of all, somebody complained that you should use the word primos because it means a same thing. So apologize for that. It is not a primos in the sense of Simber's book or Jansen's paper. We just decided to call it that. And now here P and P star are theories in and the AA logic, and these are unary predicates. It's in some sense this is like a top measure, and this is like measures on earlier stages. So maybe I right, and then I explain. So these contain in alpha times this and if beta is an alpha, then all these such that beta IA is in D is a complete consistent LAA theory, and it contains the first order theory of J prime beta epsilon and D restricted to that. T star is a complete LAA theory, complete consistent, containing first order theory of J, T, alpha, epsilon. And then there are other conditions which I will explain if I time. But so already here, I mean, typically this is a countable structure. Now, in a countable structure, of course, the AA quantifier is meaningless. But still, we can list axioms, so we can say what we would like to be true if we ever get some kind of iteration into an uncountable model, so that this AA quantifier really makes sense. This is in this E star is what we would like to be true with the AA quantifier in this, and this T predicate just tells what is true before. So so there are these levels beta and this T encodes in a sense what is true in these early stages, and then this T star talks about the final stage. It's a complete consistent theory. So we don't know what the model will be like because it's just a consistent theory. And what this is a continuous increasing sequence of unary offsets of J prime. What happens is that I describe now how from this mouse we can get an ultra product. AA ultra product. It's an imitation of ultra product, where we use these theories instead of the ultra filters that usually are used in ultra powers. And in that way, we can, if here is this initial, we can get a proper extension, and we can iterate. If we do it properly, which I try to explain, we can do it omega 1 times. And then we can prove that not only that all iterates are boundary, but there are no new reals in this iteration. So the reals of the final model, which, because we have these predicates which help us to guide so that the final model is actually an initial segment of the AA model. So if we have a real here, then all its predecessors in the canonical well order ever will be already in this model because this iteration doesn't bring any new reals. So they are all here. So it has only countably many predecessors. So there can be only one reals. So this is the basic idea, but we have to use this ultra power construction. There are some other conditions, I think 9 conditions, to make this somehow coherent, but I won't go into that. So now I define the basic ultra power. The domain of the ultra power consists of formulas such that almost all S, phi, S, for almost all S there exists an X, phi, S, X, A is in this star. So if this theory says that for a class many S there can some X, then we take this formula into this model, then we define equivalence.
But the formula you allow are just first order formula, or they have the special quantifier?
Yeah. That's of course essential. So this holds is defined to hold if and only if the claim that for almost all S. Now I use a definable spline function phi f my S X A S equals f psi S X A S. So this we add definable functions which take the minimal elements such that almost all S phi S X A. So if this element which is picked by the spline function is say in the sense of the star, then we identify it. So then the ultra power consists of all these. And we define in an obvious way this only if almost all S f phi S X A S is an element of f psi S X A S belongs to this star, etc. So we get this we get ultra power of this free mouse shape.
But how do you know that there is a canonical choice of the scaling function?
Because there is a definable well order. In a,
Even having class determinants, that's compatible with the definable well order.
well, it is such that these kind of structures, these state structures, have a definable well order.
Okay.
It's just that
So from the outside, you can see the class determinants not inside the structure.
this has nothing to do with class determinacy, so
Well, you do have, because you won't have No, sorry, apology.
Well, I will use graphical elements, yes. In when I, okay, so then there's a watch lemma. With, and there's a concept of elementary embedding, which is actually elementary embedding between two premises is so-called weak elementary, which means that it's elementary with respect to first order formulas, and for the AA quantifier, it's only for sigma zero formulas. Sigma zero in the AA. I mean, it's for this. We can only apply the AA quantifier to this star. Then we need a lemma, a kind of embedding lemma, that if I have this mouse if I have an embedding into some real real level of the AA model. So note here we have just a theory in two theories, but here we have real truth limits. So if we have this, if for example, if we started with a mouse which is an elementary submodel, so that we know this, and then we make this ultra power, then there is an embedding which makes a computing diagram like this. So if we started with an elementary submodel, then we know that it's well-founded. And now we know that then also the ultra power is well-founded. Okay, this has to be countable. And we can do this, so this way we can get this omega 1 sequence of countable well-founded models. And lemma this J prime alpha epsilon T star and the ultra power have the same reals. Meaning that every real here is the image of some real from here.
What is the role of this piece? Because like you, are this just for?
Can you start again? What is the role?
What is the role of the piece? Of the P predicates here.
Oh,
Like, are we
okay,
supposed to do
okay,
something special or is?
Very good question, because I have not yeah, because in order that this becomes a real real piece of the real AAA, I have to get away from these terrible fake theories here, which are not really true. They are not the truth theories. They are just theories how things could be. But I'm building here a continuous sequence, and now this continuous sequence becomes a club sequence because it's a continuous sequence. Becomes a club, and in fact, this embedding here is made so that always the previous mouse is the image, and the image of the previous mouse is the next P predicate. Okay, so this becomes a P predicate here, this becomes a P predicate here, and this becomes a P predicate. So in this way, this club really reflects this whole sequence. And then I can use this club to show that what this theory says at the end is really the true AA theory.
So the pieces are supposed to provide counterexample to false statement about clubs, right?
Yeah.
So you can, if okay.
That you can say that way. Yeah.
That's something.
So there is like one true club which
Okay.
is the right answer to every question about clubs. So this here is based on the fact that the club filter here is countably closed. and there are uncountable many formulas. This, because this kind of definable ultra power, and this is based on the fact that there are uncountable many reals, and the blood filter is in. So I have to assume that this is elementary submodel of some real shape vector. So then I move here. I use the real blood filter, and there are uncountable many reals, and I diagonalize them. So I already proved the continuum hypothesis. Because if I take a real, it comes from somewhere, and this somewhere has only uncountable many reals, and no new reals come. So in the end, there can be uncountable reals. There's a more complicated argument which shows that CCH. And now I can also prove why the reals are sigma 1, 3 set, because we can say that a real is in the AA model if and only if there is a mouse, iterable mouse, where the mouse thinks that it is in the AA model.
Are you dealing with just one single measure?
Yeah. Well, it's not really. It's not a measure. This is a theory.
This is the point of the algebra. Oh, he was building like model extensions. Was there an algebra involved in the algebra construction?
No. I'm talking about ultra power, talking about top measure, and so that's a metaphor, but as some metaphors are dangerous because people think that it's true.
But
So let's forget about ultra measures. This is not a measure, this is a theory, and a theory. This is the kind of a theory of the top, and this is the theory of all the previous.
So you were just building the theory from the start.
Yeah.
The model.
You build the model from here, but because of various kind of reflection type arguments, it's difficult. It's important to drag along also the theories of the earlier stages.
So once you did it once, then you cannot do it again, right? Because you need to.
No, but here you you can't do in set theory, if I may teach you some set theory. You can't do in set theory one thing. You have to do it in stages. Build the ground for doing the one thing. That's how I think about it. And this is like building the ground for this. But
so you call it ultra power because what determines what CD gives you is roughly that you will have this ultra property that either something holds in the theory, that it holds in the or doesn't hold.
because of the graph determinacy.
Kind of.
I have this like watch lemma like ultra powers, and it is used all the time. In fact, one of these axioms here is graph determinacy. That is mouse satisfies graph determinacy. So it has the resemblance of Cohen's definable ultra power, which he used to construct the first non-standard model of the history of mankind. He defined it roughly like this. But now, rather than saying that for all but finitely many something happens, like in the pressure filter of Spoon, we say that if this theory says this, so it is a little bit like ultra power. Okay, so I think I now have used my time, and I was able to kind of finish.
Could you change it to a literal ultra power? So could you, for example, define a filter on the hanging algebra, on the Lieberman algebra, and somehow make it actual ultra power using CD?
make it actual over power.
Yes, over something, let's say in above algebra.
I have not thought about it. Eh, but probably there is some kind of construction like this has appeared in logic somewhere. So it's like balancing with this theory, consistent theory, knowing that this may lead to a complete craziness, but we have this club which keeps us on the right track, because the way we construct the club is that in the successor stage, I always take the previous model as the next step in the club. So that gives a kind of coherence to this theory, and then in the end we hit the real truth rather than some most of the time.
What came first, like club determinacy or this construction?
What did you ask?
What came first, club determinacy or this idea?
I think this came first, but then there were problems because we didn't have that, and we couldn't sort of push it through. So then we got club determinacy in order to get this construction going.
Yeah, because it looks like this.
Is there a hope for diamond? Oh, diamond is true, yes. But it is open, and whether CD implies PAA satisfies the square, and in general fine structure, which would perhaps be necessary for proving this is open. So one would have to study this kind of interface much more to get the fine structure. But it has not been done.